Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing another crash course on the topic of waves for Cambridge AS Physics. There's a lot of content to cover in this topic, so we're going to move through it relatively quickly. And again, you have to make sure that you are going through your notes regularly, you are understanding the concepts and solving problems as well, which I will do at a later time. So, on the topic of waves, where do we start? Well, everyone thinks they know about waves until they actually study waves, and then it becomes one of their least favorite topics. So I'll try to simplify everything as best as we can. And we start with something called progressive or traveling waves. And there's a very specific reason why we call these waves traveling waves. And so, what is a progressive wave? Now, as the name suggests, it's a wave that, well, is moving. So if I were to state this very informally, I would say a traveling wave is a waves that move. And what do I mean by move? Well, what this means is, well, firstly, what is a wave? A wave is created when there's a disturbance in a medium. If I bang on this desk, for example, I'm going to generate a sound wave. I disturb the atoms of the desk, which disturb the surrounding air molecules, which create a sound wave that travels outward in all directions, and I can hear the resultant wave as it creates a disturbance in my eardrums. So any disturbance in a medium is how a wave is generated. We'll learn later on that a medium is not always necessary, but basically waves that carry energy from one place to another, just like the sound waves does. The sound waves will carry energy from the source to the receiver, and so it is a traveling wave. So the energy travels, quote unquote, from one place to another, and this is a traveling wave. So we're going to start off by describing traveling waves, because if you've already done the topic or in the middle of the topic of superposition, you'll know that there are things called stationary waves that don't carry energy from one place to another. So what type of progressive waves do we have? Well, we're going to deal with two, and the first is called a transverse wave. The first type of traveling wave is a transverse wave, and in a transverse wave, we have that the particles that are vibrating, that have been disturbed, they move or they vibrate perpendicular to the direction in which the energy is moving. So remember, we said energy is moving, but if the particles that make up the wave are moving perpendicular to the direction of energy, then this is a transverse wave. So vibrate perpendicular to the direction in which energy is moving, or we can also say the direction of propagation. The word propagation means to move. That's an easier way of saying it. And so what does this look like? Well, let me see if I can represent this with a simple diagram. So let's imagine this diagram that I have drawn here. Let's imagine this to be a water wave in the ocean, and I'm looking at it from side on. So I'm going to use blue because, well, ocean, water. And so in this example, here I have a water wave. I'm looking at it from side on. And in this water wave, what I actually have is that water molecules, or a particle of water, is moving up or down. And so if I were to look at a very specific molecule of water and I zoom in on that molecule of water, what I notice is that this molecule is moving up and down. But also, as I'm looking from side on, what I notice is that the wave moves from ocean to shore. And when the wave reaches the shore, it crashes into the shore and releases some of that energy, and the wave moves up the shore until it can't go any further. And so the vibration or the motion or the oscillations of the particles is up and down, but the direction in which the energy is being carried is towards the shore, which is why tsunamis are so devastating, because the energy of the large waves are carried onto the shore. And so what I can see is that vibration happens up or down, energy moves left to right, these two are perpendicular. So this is an example of a transverse wave. The other type of wave that we have is a longitudinal wave, the other type of traveling wave. Now, a longitudinal wave also has particles that are vibrating, but the particles that have been disturbed, they vibrate parallel to the direction in which the energy is moving. So I say the particles vibrate parallel to the direction of propagation of the wave, or parallel to the direction in which energy is moving. So you can see that it would look slightly different from the picture that I have above. It's still a wave, but the idea would be different. So let's take an example of a sound wave. Turns out sound waves are a good example of longitudinal waves. So let's say I have a source of sound, a speaker. Again, this example is of a sound wave. And this source of sound is vibrating. The speaker itself vibrates. As the speaker vibrates, it disturbs the air molecules around it. Now, what happens is the air molecules don't move up or down, as the water molecules did in the water wave, but the air molecules move left and right. And at some positions, the air molecules get very close together, which we call positions of rarefaction. And then at some positions, the air molecules get very far apart. And then the pattern sort of repeats itself. And so if I were to zoom in on a specific air molecule, and obviously for the source we have to have a receiver, and I'm going to try and draw, believe it or not, that's an ear. Since it's so poorly drawn, I have to label that. That's my ear. If I zoom in on a specific air molecule, what I find is that the molecules vibrate, in this case, as I look side on, left to right. And so as one of the molecules vibrate, they disturb the next one, passing the energy onto it, and so on. And so the energy moves from source to receiver, and the energy also moves from left to right. So that you can see the molecule, the particles that are vibrating parallel to the direction in which the energy is moving. And so the particles and the energy are parallel, and we call this a longitudinal wave. So you can see that the longitudinal wave is very different from the transverse wave. In the transverse wave, the particles vibrated perpendicular to the motion of energy, and in the longitudinal wave, the particles vibrate parallel to the direction in which energy is moving, or in which the wave is propagating. So the next thing we need to do is represent these graphically. We need to be able to look at a graph of probably displacement versus time, or even displacement versus distance, and be able to understand fundamental features of a wave. So how do we represent a graph of a wave? So the first thing we'll do is define what displacement is. Now we know what displacement is as a vector when we learned it in dynamics and kinematics, but what does it mean for a wave? Now, when we talk about displacement, we are talking about the particle that is vibrating, any specific particle. So the displacement is the distance that a specific particle moves, and in a given direction, because it's a vector. So we have to consider direction. And so for the water molecule that we've seen above, if it moves up above its central point, we can call that positive, just by choice. And then if it moves down, we can say that displacement is negative, below its central equilibrium position. And so what does this look like graphically? Well, believe it or not, I can actually represent the graph exactly as I would represent the water wave. So I'm actually going to use just the same diagram. And so this graph looks something like this. I need a y-axis to go along with my x-axis. And remember, this graph applies for both longitudinal and transverse waves, even though it looks more like the side-on view of the transverse wave that we saw. But I will give this y-axis the title displacement. So I'll call it displacement y. And on the x-axis, I will plot distance. And so that means displacement being where the particles are at. So there's my water molecule at the crest of this wave. And again, the water molecule is moving up and down. The energy flow is from left to right. And I'll just draw this again so that you can see. So vibrating up and down, energy moves left to right. We can use the example of the water wave, but this also applies to longitudinal waves. So what this means is the distance, well, if I'm looking from left to right, the distance is the distance from the start of the wave as I see it to the shore, from the furthest point of the ocean on the left to the shore on the right. And that's how much of space the wave is occupying, whereas the displacement only refers to the particle's motion. The maximum displacement that the particle can have is called the amplitude. And the amplitude is always the distance from the central position, which we call the equilibrium position, to the highest point or even the lowest point in the wave, of the wave. And so this is called the amplitude, which is the max displacement, the maximum displacement. The highest point in the wave we usually call the crest, and the lowest point we usually call the trough. So if I use these words, which again you'll find in any good textbook, you know exactly what I'm talking about. The distance over which a particle will do one complete cycle, that is, if I start at this point, I go up, come down to the equilibrium position, go through the trough and come back to the initial position in which I started, that distance is called the wavelength of a wave. And so the wavelength is the distance for one complete cycle. We can also call this a cycle. The distance of one cycle of a wave. Any 2 points that are in phase. We have to talk about what in phase means. So actually, if I think about any 2 successive crests or successive troughs, those 2 points are also where the particle is doing the same thing. And since they are doing the same thing, the 2 points that are successive to each other doing the same thing is a wavelength. So you'll notice that the 2 distances are the same. The wavelength of the wave shouldn't change. And so the distance from where I draw the solid line is a wavelength, but also between 2 successive troughs or 2 successive crests is also the wavelength. And yeah, this is a graph of displacement versus distance. Okay, just be careful. This is not time on the x-axis, but this is, and I write time. Wow. This is a graph of displacement versus distance. So y versus x. And so this is what my graph of displacement versus distance would look like, irrespective of whether this is a longitudinal wave or a transverse wave. And that's because the displacement of the particles in a longitudinal wave will also have an amplitude, have a maximum value in one direction or the other, while the wave can be moving in the x direction, can be moving from left to right. And then obviously the other graph that I can draw, since I've already drawn displacement versus distance, is, you probably guessed it, but displacement versus time. So I'm going to take the same idea and I'm going to apply it to the graph again, but I'm now going to use the y-axis to be the displacement again, but the x-axis is going to become, the horizontal axis is going to become the time. And so the horizontal axis is the time t. So we got a graph of y against the time t. So if the particle is oscillating or vibrating, its maximum displacement is still measured by the y-axis, so this is still the amplitude. But I can't measure a wavelength on the horizontal axis because on the horizontal axis I don't have a distance, I have a time. And so by definition, one complete cycle, which I've shown here, also the distance between two successive crests and two successive troughs, we call the period. And we give it the symbol uppercase T. And the period, notice the difference between uppercase T, which is a fixed constant, which will never change for this wave, and little t, which is a variable, time. So the period is the time for one complete cycle. So every cycle should have the same time, and we call that time the period. It's a constant for a given wave. And so we learnt a new quantity, the period. We also have another quantity called the frequency. Frequency basically means how often something happens, and it's the same for waves. And the frequency is the number of oscillations, or the number of vibrations, or the number of complete cycles in a unit time. How many times do I expect the wavelength of the wave to pass every second? The more waves pass every second, the greater the frequency. Fewer waves that pass every second, the lower the frequency. And so I can see that the period is actually the inverse of the frequency, because the period is the time that it takes for one wave to pass, which is the inverse of how rapidly they pass. And so if I use square brackets to denote units, the units of period is the second, it's measured in time, and the frequency, which subsequently is also the inverse of the period, has a unit of measurement which is per second, but we give it a different unit of measurement, a derived unit, just to denote that we are talking about frequency, which is called the hertz, uppercase h, lowercase z. And so the unit of frequency is the hertz. How many waves are moving past a point every second? I'm standing at side on towards the ocean and I notice many waves passing per second, then the frequency is high. If I notice very few waves passing through a certain point per second, then the frequency is low. And low frequency means high period, and obviously high period means low frequency. The next thing we need to learn about waves is the phase and path difference. And this might be something new to most of you. And so the first thing we're going to do is we're going to describe the phase and path difference in terms of some circular motion, kind of going off track slightly. Now imagine a particle moving in a circle. And I'll tell you why we are considering a circle specifically. But it turns out we can represent these wave-like oscillations by a particle moving around in a circular path. And so here I have my particle. Any given time it's moving to the right. In this case it's rotating clockwise. And so it's moving in a circular path, circular enough for freehand. So it's moving clockwise, and if it does one complete cycle, it has covered an angle of 2 pi radians. It's covered 360 degrees. If you walk around in a circle, you've walked through an angle of 360 degrees. You should have studied radians by now. If you haven't, 360 degrees is 2 pi radians. You will learn that at some point. And so what we do is we apply this to wave motion. Well, we say let one cycle, for convenience sake, I mean, the wave's not moving in a circle, but let's assume that one cycle, which is one wavelength, is equivalent to 2 pi radians. It just makes it easy to denote the motion of waves when we apply the same logic to waves, the circular motion example. Now, any two particles on a wave that have the same displacement at the same time are in phase. We say that the phase difference between these two particles is zero, the 2 points in the wave. So if the displacement of two water molecules on my water wave are the same at the same moment in time, if I take a photograph and I look at two specific water molecules both doing the same thing at the same time, we say that they have a zero phase difference, hence they are in phase with each other. And they need to be moving in the same direction as well. So I have the same displacement but moving in the same direction. So if I take a picture of a wave and I look at the two water molecules at the crest, at two subsequent crests, or any two crests of the wave, those two water molecules are in phase. They have the same displacement and they're moving in the same direction. And so what does this mean? I'm going to have to go back and get my graph since I'm too lazy to draw this again. And so here's my graph, my wave, and I'm going to try and represent this graphically. So let's take 2 points on the wave. I'm going to take a random point here, A, and another random point, B. If you keenly observe this, you can see that these two particles have the same displacement from the equilibrium position, and they happen to be one wavelength apart. So the distance between A and B is one wavelength, and what this means is that they are moving in the same direction. So they undergo a full cycle, or a particle separated by a wavelength from another particle moving in the same direction with the same displacement. So if this is a graph of displacement versus distance, then YA is equal to YB, and this means that A and B are in phase. Now the opposite of in phase is out of phase, and 2 points will be out of phase when they are half a wavelength apart, when they are separated by half a wavelength. So if you look at C and D, one's a trough, the other's a crest. One is moving upward and the other is moving downward. And their displacements are, well, the opposite of each other. D is the amplitude, C is minus the amplitude. It's a negative amplitude. And so what we say is, since they are completely opposite to each other, they are completely out of phase. And so any 2 points doing the opposite thing at any moment in time, we say are out of phase. They are not in phase. And they are separated by half a wavelength, any integer multiple, as we'll see, of half a wavelength. And so what we see is that any wavelength can then be defined by points in phase. So the wavelength is the minimum distance. If I want a correct definition, is the minimum distance between 2 points in phase, meaning the distance between two successive points in phase. So any 2 points in phase, if I take the minimum distance between points in phase of a wave, because there'll be many of them, The smallest distance will be the wavelength of the wave. So the wavelength is the minimum distance between any 2 points in phase for that wave. So what does it mean for waves to be in phase? So how can I show that any two waves are in phase? Well, for any waves that are in phase, I have a path difference. Now, a path difference is equal to the distance xb minus xa. So whatever's on the horizontal axis, the distance between two particles in a wave, how far one particle is from the other. And this distance must be an integer number of wavelengths, n lambda, where n is any positive integer value, 0 or any positive integer value, 1, 2, 3, etc. And if the distance between two particles is any integer number of wavelengths, these 2 points on the wave are in phase. Now, how do I convert this to a phase difference? Now, there's a difference between path difference and phase difference. And remember, I said lambda is equivalent to 2 pi radians from our circular motion example. That means the phase difference is n, an integer value, times 2 pi. And again, n is 0, 1, 2, etc. So for waves to be in phase, they must be a whole number of wavelengths apart. The opposite of this is waves that are out of phase. So for waves to be completely out of phase, we must have that the distance between two particles of that wave, in our case, was xd minus xc for the example I did above, and this must be half an integer value of wavelength, so half n lambda, and n again is 0 and any positive integer value, 1, 2, 3, etc. And subsequently, the phase difference, if I let lambda be 2 pi, is a half n 2 pi, which I can simplify and write this in a better way, n pi. So any integer multiple of pi, that's 180 degrees, and 2 times 180 degrees, and so on. Right? Actually, we want the path difference and the phase difference to be odd multiples of lambda, or odd multiples of 2 pi. So we have to ensure that n is odd integer values, 1, 3, 5, and so on, so that we get exactly half a multiple of wavelengths. And so for the phase difference would also be a half n times 2 pi, which is n pi where we only consider n to be the odd integer values. So we have 180 degrees and 180 plus another 360, which is 450, and so on. And at these distances, or at these phase differences, the 2 points are completely out of phase. So that's a difference between the path and phase differences for waves that are in phase and waves that are completely out of phase. So let's look at an example. So here I have 2 graphs, and it's clear that both these graphs have, or both these waves rather, have the same frequency. So we've kept the frequency the same, which we need if we are to measure the phase and path difference of these 2 waves, and they also have the same amplitude. They need not have the same amplitude, but again, that makes it just easier for us to compare. So I'm going to deal with the blue wave first, and I'm going to count the time on the x-axis, or the horizontal axis. So the time for one wave is t, and then the time for 2 waves, the period is 2 periods, which is 2t, and so on. Now what I'm going to do is, if I'm measuring displacement on the y-axis, I'm going to take 2 points that are in phase. So I'm going to use the 2 subsequent points between the orange and the blue graph. And since I know those points are in phase, I'm going to count the time difference. So this could be 2 water waves traveling on the same body of water. The first one, the blue one, moves past, and a little while later, after some time delta t, the second wave moves past. So what I want to do now is calculate the path and phase difference between these 2 waves. So if I take, for example, again this is an example, the period of the wave to be, let's say, 4 seconds. I'm just choosing an arbitrary value here. And the time difference between the 2 troughs passing me happens to be 0.5 seconds. Then what I can do is calculate the phase difference. And the phase difference is the fraction of the time over the period that it takes for the same point on either wave to pass me, and then to multiply that by 2 pi, which is the path difference multiplied by 2 pi. And what I get is 0.5 divided by 4 times 2 pi, which I get is pi by 4 radians, and so the phase difference is 45 degrees. So essentially, if I were to think about this in circular motion, one particle would have done 45 degrees angle around the circle, 1/8 of the circle, before the second particle starts its motion. And so they'll always be 45 degrees out of phase, since the waves are traveling at the same speed. And so, talking about speed, that brings us to the next part, which is the wave equation. And now we have to start talking about these quantities that we've been thinking about, but we haven't actually defined as yet. So the speed of a wave can simply be thought of as the speed of a single particle of the wave. And the speed of the wave is the distance x divided by the time t. So how many waves, or what the distance of the wave is per unit time. How far has the energy been carried per unit time? So for one complete cycle, the speed is the distance, which is one wavelength, divided by the time t. So as I'm watching this wave, I see one wave go past in a time t, which we call a period, uppercase T. And so V is lambda divided by T. But if you remember, we said that 1 over T, 1 of the period, is the frequency. So the speed is the frequency multiplied by the wavelength. So what this means is, since the frequency and wavelength of the wave is not changing, at least in our case for now, that the speed of a wave in a specific medium must be constant. So the water wave should remain at constant speed, provided we don't change the frequency and wavelength. We'll learn later on that the wavelength can change, but the frequency can only change at the source. The other quantity that's important to discuss is the intensity. We're not going to discuss this in too much detail, but the intensity of a wave, I, is defined as the power of that wave, which is the energy per unit time, if you remember power from dynamics, divided by the area over which the wave is providing that power. So obviously larger area means smaller intensity. So the intensity is the energy per unit time per unit area. And the thing that you need to remember, we're not going to derive this or even write this equation down, is that the intensity is proportional to the amplitude squared and also proportional to the frequency squared. So A here is amplitude and not area, so I'm just going to write it down. So the intensity is proportional to the amplitude squared and to the frequency squared. It's a common exam question to ask, well, if I do something to the amplitude, how does this affect the intensity? Or vice versa. If I do something to the intensity, how does this affect the amplitude of a wave? And so that's just a little bit of extra info there for the intensity, which you need to know. Now we need to move on to some properties of waves, and specifically properties of wave motion. So there are certain properties that waves can undergo that particles generally do not. And the first one of these is reflection. Now, for reflection, a wave must strike a barrier or a boundary between two different media, going from medium 1 into medium 2, but the wave doesn't move into the second medium. It simply, reflects, or to say it better, it changes direction and stays in its current medium. So that would be light striking a mirror. Instead of moving into the mirror, the light reflects and bounces back and stays in air where it was initially. That's an example of reflection. So we can represent a wave by something called a wave front. I'm defining this now because I'm going to use wave fronts for the next little bit. And a wave front is, you can think of it as a line of points in phase. So if I'm looking from the top down, this could be the crest of a wave, and it is multiple points that are on this crest. So it's a two-dimensional point. So any line of points in phase we can represent by a line, which we call the wave front. And so there's a whole lot of crests here. And so I'm going to draw many of these wave fronts. The distance between any two successive wave fronts is the wavelength. They're meant to be equally spaced, but I've kind of drawn them poorly. Let's try and ensure that they're relatively equally spaced so that the wavelength remains constant. I then include a barrier. Something, if this is a water wave, it could be a piece of wood, etc., that I have maybe in a ripple tank. And as the wave strikes this barrier, the wave is going to change direction, as it can't move through the barrier, it can't overcome this barrier, and so it changes direction, and it starts to move off in that direction. So initially, the direction of motion was that way, and then after striking the barrier, the direction in which the wave is moving is that way. And so this is an example of reflection. And an extra property is that the angle that is made here by the incident wave is I, and the angle made by the reflective wave is R, and it turns out that these two angles are equal. And so this is an example of reflection. Now it's important to know what happens during reflection. If you look at the wave very carefully, again I haven't drawn it very well, but the wavelength of the wave does not change. So the wavelength remains constant after reflection. The speed of the wave remains constant since it's traveling in the same medium through which it started. The frequency remains constant. The frequency also can only change at the source, the thing that's creating the wave. The only thing that really changes here is the direction. Even the medium stays the same. The direction of the wave changes. It was initially moving to the right, and now it's moving, as we look at it, upward. And so that's the wave property of reflection. The only other property that we're going to study, at least for now, is refraction. So this is also a property of wave motion that's slightly more complex, but not excessively so. I have a wave, which again I'm going to represent by wave fronts, moving towards a barrier or a boundary. I'm going to call this a boundary rather than a barrier, because in this case the wave can overcome this boundary and it will move off in a direction that is different to its original motion, but also it's going to move into the second medium. So maybe the first medium is air, or for a water wave, maybe it's water of a shallow depth, and medium 2 would be water that has a greater depth. And this dotted line is the boundary that is separating the two media. So initially the wave is moving to the right, strikes the boundary. What happens then is it moves into the second medium. It moves into the second thing through which it can travel. It changes direction, but it also changes speed. So the speed changes depending on what the two media are. But when the speed changes, since the frequency cannot change, and v is equal to f lambda, the frequency can only change at the source. So that means that the wavelength must change as well. So the wavelength of the wave changes. Maybe I should represent this slightly better. You can see that the wavelength of the incident wave and the refracted wave are different. The wavelength changes, the speed changes, but the frequency must remain constant. The number of waves that I see passing a given point per second must remain constant. That can only change when the source of the wave creates disturbances at a different rate. And so that's the wave property of refraction. The next thing we need to talk about is the cathode ray oscilloscope. So I'm just going to show you what the cathode ray oscilloscope looks like so that you know how to identify how we use it to calculate different quantities related to waves. We also call this the CRO, which is probably what I'm going to refer to it as from now on. So this is what the CRO display would look like. So it's, again, just a graphical representation of my wave, but has a grid associated with it. And it doesn't have a horizontal axis because the display on a CRO can change. Or rather, the axes can change. So we can move this graph around. And so the axis doesn't remain fixed as it would if I was drawing it on a piece of graph paper, like I am now. So essentially, I have a Y setting and I have an X setting on the oscilloscope. These are not physical lines drawn. They have to be chosen by the user of the oscilloscope, and they are arbitrary. And each one of these blocks, in the case of a CRO, will represent maybe a centimeter. So each one of these grid lines would be a centimeter in distance, in length. The amplitude of the wave is still A. The period of the wave, because the X setting is usually time on your regular CRO display. And so the time, the distance between two successive peaks, if I measure the time, will give me the period. But another important quantity is this value that goes from the crest to the trough, and we call this the peak-to-peak value. Generally, it's voltage, since we usually have on a CRO the y-axis giving us voltage. So the Y setting is what we call the voltage base, meaning I get a voltage representing my amplitude, and it's measured in volts per centimeter. And the X, or the horizontal setting, is usually called the time base. So the time base meaning it measures time. So I have not displacement of the y-axis, but a voltage. And this is measured in seconds per centimeter, 1 second for every one of these blocks. And on the y-axis, 1 volt for every one of these blocks. The difference is with the CRO, we can adjust these settings. We can adjust it so that the graph is large enough that we can actually read the values of amplitude and period, etc. So we have to calibrate the CRO before we can just go ahead and use it. So if I wanted to find the period, it's a common type of exam question. I take the number of centimeters on the x-axis. So this is just like an algorithm, if you would like, to calculate the period. The number of centimeters on the x-axis from crest to crest, for successive crests, obviously, or from trough to trough, or any 2 points in phase. Preferably crest to crest or trough to trough. It's easier to use to measure those. I'm saying crest to trough, that's crest to crest. Successive crests. I take that distance in centimeters and I multiply it by the time base setting. So I have a value of centimeters multiplied by the time base centimeters second per centimeter, and I'm left with a value of seconds, which is the unit of measurement for time. If I want the amplitude, in volts that is, I take the number of centimeters on the y-axis, but I have to be very careful. I don't have a plotted x-axis on my CRO display, as you may have seen from your examples of past exam questions. So I have to take the peak to peak value, that is crest to trough or trough to crest, up to down. I have to take the value of the peak to peak reading, which I can read on the oscilloscope, and divide it by 2, and then multiply that by the voltage base. So I have the number of centimeters on the y-axis, the peak to peak reading. I divide it by 2, which gives me the amplitude, and then I multiply it by volts per centimeter. So the centimeter and the per centimeter disappear. I'm left with an amplitude. But just remember that this amplitude is measured in volts, because the y base setting is volts for a CRO. The next topic is usually one that's novel to people studying, well, physics in general, and that's the Doppler effect. Now, we've all come across the Doppler effect in some way or the other, we just didn't realize what was happening. Now, the Doppler effect is the apparent shift in frequency when a source of sound is moving relative to an observer. You all have heard an ambulance or a police car moving towards you or away from you, and the pitch of the sound created by the siren is higher when the car is moving towards you or the ambulance is moving towards you, and lower when the vehicle is moving away. So the first case is what happens when there is a stationary source of sound, that is, your ambulance or police vehicle is stationary, and you are a stationary observer. Well, what happens in this case? So let's assume the source is at the center. Here, the source of sound is at the center. And then I have my observer, which is me, stationary. The circular lines represent wavefronts. And what I can see is that a sound wave obviously moves out in a circular pattern. It moves out equally in all directions. It doesn't only move in one direction. And it moves at the same speed, so that's why it travels in a circle. And so these dotted lines represent the wavefront. This means that the distance between successive wavefronts are the same. So lambda is equal to lambda is equal to lambda. These wavelengths are all the same. And so what I notice is the sound doesn't have any difference to the person at the source, the paramedic or the police officer, as it does to the observer. The frequency, the pitch, the wavelength of the sound remains the same. A wave is emitted, and then a few seconds later, whatever the frequency and the period is, the second wave is emitted, and so on. And so what does the observer notice? Nothing fancy. The frequency remains the same. But what happens in the case that the source is moving? So I now have that the ambulance is taking off, and so we have a moving source, but we're still only going to deal with the stationary observer. For A-levels, we only deal with a stationary observer. So what happens then? So if you look at the picture, you'll notice that the picture is quite different. So now I have my source at the center, but I have two observers. I'm going to label them A and B. The source is moving to the right, and we say it's moving to the right with the speed Vs, and the frequency that's being emitted by the source is Fs. What we notice is that the wavelength is not the same on either side. The observer B is in the path of the ambulance. The ambulance is moving towards observer B and moving away from observer A. So as the source of sound, as the ambulance moves towards observer B, it emits a wave, moves a distance, and emits the second wave. And as it's moving, the wavefronts decrease in wavelength lambda, and we can see that the wavelengths decrease towards observer B. And observer B observes a frequency FO. Since the wavelengths are decreasing, the frequency actually increases. So the observer at B observes a higher frequency. Remember, this is an apparent frequency. It's not the frequency of the ambulance actually changing, it's the frequency that's observed at B. So in this case, the observed frequency FO is greater than the frequency of the source. While at A, it's the opposite. These wavefronts are stretched out. The source has moved a distance before the next wave has been emitted, and so the distance of the wavelength rather increases. So the apparent wavelength lambda A is now stretched out compared to the original wavelength of the wave. And so this observer also observes a different frequency, but it is lower. So the pitch of the sound is also lower. And so a higher frequency is observed at A, but a lower frequency is observed at a higher frequency at B and a lower frequency at A. So the observed frequency is less than the source frequency. Remember, all this time, the frequency of the ambulance's siren hasn't changed. It is the apparent effect because the source is moving relative to the observer. And so, mathematically, we can write an expression to calculate this observed frequency. Since it's not the same as the original, we have to know how to calculate it. So, I won't derive this equation. We'll leave that for another video. But if the source is moving towards the observed frequency is equal to the frequency of the source multiplied by the speed of sound in air. Remember, the speed at which the sound wave travels depends on the medium, which is air in this case, divided by the speed of sound in air minus the speed at which the source is moving. This is moving towards the observer. So here I'm going to write down FO is the frequency observed by observer B in this case. We simply call it the observed or apparent frequency, so since it's not the actual frequency. Fs is the frequency of the source. V here, simply V on its own, is the speed of sound in air or the speed of sound in whichever medium the source is traveling in. And Vs is the speed at which the source of the sound, or the ambulance in this case, is traveling. And so this is the equation of the Doppler effect when you want to know the observed frequency when a source of sound is moving relative to the observer. Now what happens if I'm considering observer A? What if I'm moving away from the observer? So it turns out this equation changes very slightly. The observed frequency is still the frequency of the source times the speed of sound in air, but the denominator becomes v plus vs. And what we can see is that this value is a smaller value than the one above. So if I'm moving toward the observer, I have a minus sign in the denominator to make the observed frequency higher, since the ambulance is moving towards me. When the ambulance is moving away from me, I add a plus sign in the denominator so as to ensure that the observed frequency is lower. And so the minus and plus signs are a hint the object is moving toward, the source of sound is moving towards the observer. It's a minus sign. If it's moving away from the observer, it's a plus sign in order to keep the size of the observed frequency correct. So next we're going to move on to electromagnetic waves, which, as we know, behave quite differently from the waves that we've been talking about thus far. Now, the main thing about electromagnetic waves, at least when you first learn them, is that they don't need a medium. So electromagnetic waves can travel in the vacuum of space. They don't require a medium to travel in. It's very different. And you'll learn later on in A-level physics that the disturbance still exists, but the disturbance is a very different type of disturbance. The electromagnetic waves that we can see are what we call visible light waves. And that's the only waves that are visible, at least for us. And so we simply or informally call them light waves, or simply light. And they travel at a constant speed in vacuum and, well, basically in air as well. The speed doesn't change much between vacuum and air, but the speed is the speed limit of the universe. It's 3 times 10 to the 8 meters per second. And this is the same for vacuum as it is for air, roughly. There isn't much significant difference between the two media. And so this is what the electromagnetic spectrum looks like. Now, I'm not going to go through this in detail, but you need to know what the electromagnetic spectrum looks like. On the left-hand side of the graph, we have low wavelengths and high frequencies. And you can see low wavelengths and high frequencies correspond to cosmic rays, cosmic radiation, gamma rays, X-rays going up towards ultraviolet, infrared, and then into the visible light spectrum. The visible light spectrum is the one that's expanded above. And the range of wavelengths for visible light, and this is another fact that you need to know, is between 400 nanometers, which is violet, to 700 nanometers, as you can see in the diagram, which is red, closer towards infrared. That's the only range, which is a tiny band that humans can actually perceive. And then we go on to higher wavelengths, meaning lower frequencies, and hence lower energies as well. Infrared, microwaves, radio waves, and then higher wavelength radio waves. And these are all different types of electromagnetic waves, which are categorized by their wavelengths and frequencies. High wavelengths mean low frequencies and vice versa. And so you need to know the spectrum from one end to the other. You could be given a certain type of wavelength and asked to describe or state what type of wave is represented by that wavelength or even by that frequency. And so that's a bit of reading for you to do. The next thing we want to talk about is polarization. So what does it mean to polarize a wave? Now, we're generally going to talk about electromagnetic waves, but polarization is, well, a property of all types of waves. So let's use the example of, in this case, I'm going to use a rope, and I'm going to create vibrations in this rope that are vertical. So I'm going to move the rope in a way that the rope vibrates vertically as I look at it. So if the vibrations of the rope are vertical, then we call this a plane polarized wave, since it is all the particles on the rope are vibrating in a vertical plane. So it is polarized in the vertical direction. It only has one plane of vibration. If I pass this rope through a vertical slit, what I find is that the wave will pass through as it entered. There will be no loss in this wave. It's going to move straight through the slit and continue moving. However, if I then shift the way I'm moving this wave, the way I'm moving this rope, so that the vibrations are horizontal rather than vertical. So think of it as on a horizontal plane. It's still a plane polarized wave, but now the plane is a different plane. It's a horizontal plane. But being polarized simply means that it's moving along one plane. But now if I have the same vertical slit, what happens is the rope reaches the slit but doesn't pass through. What I see on the other side will just be a straight line. And that's because the slit is not wide enough to allow the horizontal waves to pass through. It's a very narrow slit. I'm exaggerating the size, but it's a very narrow slit. And so only a straight line passes through. The wave doesn't travel through this vertical slit. This whole process is called polarization. Now, if I consider a wave that I have oscillations in all directions of motion, or I have vibrations not in one plane, but in a variety of planes rather, and I have the direction of energy flow, the direction of propagation of the wave, to be, in this case, I'm going into the page. What I can see is that the vibrations are happening in a vertical plane, but in different directions. So the direction of energy is still perpendicular, but the direction of the vibrations is happening in all directions. So what we say is that this is an unpolarized wave. So when we had the polarized wave on the rope, we had it in one direction, either horizontal or vertical. But here we have diagonal, horizontal, vertical, and so this wave is not polarized. There are vibrations happening in all directions. So it's the equivalent of me moving the rope in all different directions. So the energy is still moving to the other end of the rope, but it's moving, the actual particles in the rope are moving in different, or vibrating in different directions. On the other hand, if they only have the vibrations moving up and down, like I did for the rope initially, and the direction of energy is perpendicular to this vertical plane, if it's a straight line perpendicular or normal to this vertical plane, then we call this type of wave a polarized wave. So a lot less chaotic. I only have the oscillations or the vibrations happening in one direction. And so that's the difference between an unpolarized wave and a polarized one. Which then brings us to the last part of the topic, which is Malus's law. And this, we require the explanation of polarization to be able to explain Malus's law. So I'm going to take the example that I have unpolarized light. So I'm going to have light waves. I'm going to use specifically light waves here. So we're applying this law specifically to light waves. So unpolarized light, as you know, or as you may know, the electromagnetic wave is an oscillation of electric and magnetic fields. And so let's say whatever the particles of a wave, of an electromagnetic wave are, they are moving in or vibrating in all different directions. And so I have unpolarized light that I'm going to use through some filter. I then pass this unpolarized light through a thing I call the polarizer. And you can imagine why I call it a polarizer. It's meant to be circular, but you get the gist of what I'm doing. And I'm going to draw horizontal lines on this polarizer because the horizontal lines tell me which direction of vibrations are allowed. So this polarizer is only going to allow, it's created in such a way with certain crystals that it's only going to allow horizontally polarized light to pass through the polarizer. So after the polarizer, what I get is only the horizontally aligned vibrations passing through. And so what I get is, like I did for the rope, I have plane polarized light coming through. And the intensity of this light I'm going to call I0, I with a subscript 0. This light then continues on its merry way. It passes through another polarizer, which we now call an analyzer, and we align this analyzer at some random angle. Okay. So the second polarizer is called an analyzer. It's allowing light to move. In this case, I have it at some slanted angle, and we call this angle theta. So this angle to the horizontal with which the analyzer is slanted, we call it theta. And what I'm left with is plane polarized light, but in that direction. So remember, the plane polarized light that is horizontal will have a component in that direction, the diagonal direction. So again, I have plane polarized light, but I also have a lower intensity, and that's because I've sort of eliminated some of the light, but only allowed the light that has some diagonal component to pass through. And so this intensity that passes through, we call I. And so Malus's law mathematically says that the final intensity I is equal to the initial intensity that passes into the analyzer I0 times the cosine squared of the angle theta. And so mathematically, what I can see is that the analyzer and polarizer are at the same angle, theta equals 0 for both, then I is equal to I0. The light that passes through the first polarizer will all pass through the analyzer. But if I adjust the angle theta and I move it towards 90 degrees, then the resultant, or the intensity that passes through the analyzer, slowly decreases. And if the angle theta is equal to 90 degrees, cosine of 90 is 0, no light will pass through the analyzer. And so mathematically, this was Malus's law. Now, this was a lot to absorb. There's a lot of content in this topic, but it sets you up for many other topics, specifically in AS superposition, but also in A-level physics. And so the knowledge of waves is paramount. It's fundamental to understanding physics in general, not just A-level physics. So I hope you found this video useful. I know it was a long one, but if you did find it useful, please drop a like, drop a comment. Let me know what you think, if I can improve, how I can improve, and if there's any specific content that you would like on the channel. Until next time, on Everything is Relative, I'm Mr. K.